Good afternoon once again. My name is Arnold Young. I welcome you all back to the YouTube channel. And in the previous lecture, we derived the general equation for conductive heat transfer. What did we say the equation was? It was del x of the expression, that is K subscript x, that's the thermal conductivity along the y-axis, del T, which is the temperature gradient, plus del y of ky del T del y plus del z kz del T del z plus G dot. And what is G dot? G dot is basically the what? That's the heat generated within the control volume per unit volume. That's the rate of generation of heat within the control volume per unit volume. And this is equal to, that is rho Cp, which is the heat capacity, times del T del small t. This was the general equation for conductive heat transfer. Now we made some assumptions. We said that what if our material is, that is isotropic. And what did we say isotropic materials are? That is materials with thermal conductivity being the same along every axis. That is it for isotropic material. For isotropic material, then it becomes K will be the same throughout. So you can factorize K out. Then we ended up with what? That's the del squared of the temperature field del X plus del squared of the temperature field del Y, del X squared, del Y squared, del squared temperature field del Z squared plus G dot is equal to rho Cp del T del small t. Now we said that if you have something like this, what does it mean? It is basically the what? It is basically the grad squared of the temperature field. That is it. So you can write this at the grad squared of the temperature field plus G dot is equal to rho Cp del T del small t. Then we divided through by K. Right? We divided through, but wait. Yeah, it's not supposed to be negative. I wasn't writing negative. Not supposed to be negative. Yeah, we divided through by K. After dividing through by K, what did we get? Ended up with J dot on K is equal to rho Cp on K del T del small t. Then we know that as the thermal diffusivity is K over rho Cp. So it becomes that J dot on K is equal to 1 over alpha del T del small t. So this is also the equation, but here the material is isotropic. The material is isotropic. Now today I want us to derive the general equation for finding, that is the heat flux or the heat transfer through a plane wall. Through a plane wall. So yeah, so let me say the heat conduction equation through a plane wall. Now here we are going to make some assumptions. We are going to assume that one, it is obvious our material is isotropic. So isotropic material, that is our first assumption. Now what else? We have a steady flow, which is, fairly practical. It happens in practice. Steady flow heat transfer. What other assumption can I make? That is no heat generated within my control. So I should say the internal volumetric heat generation is 0. Internal volumetric heat generation is 0. then it is a one-dimensional heat flow. It is a one-dimensional heat flow. Now, let me give you a typical drawing of a plane wall. Say you have, this is the plane wall. This is the plane wall. This is my plane wall. Now this is my plane wall. This is my plane wall. Now, assuming heat is being transferred, or heat flowed through this particular this particular wall, that is from this part, that is cutting this cross-sectional area perpendicularly to this part, that is also cutting this cross-sectional area perpendicularly. So for that is steady heat transfer, then if here is Q, then this is also supposed to be Q. So Q dot, Q dot. Now this one thing I will do. I am going to draw the diagram from here, viewing it from this side. But viewing it from this side, this is what I see. I see this particular view. That is what I'll be drawing. The thickness of my wall will be represented with L. That is what I'm using to represent the thickness of my wall. Now let's continue. Now drawing that particular view, then I can say that that view looks exactly like this. Right now, this particular phase was at some temperature. That particular phase was at some temperature. Now we are saying we have, that is a steady flow heat transfer. So meaning our temperature doesn't vary with one, time, and also varies along only one single spatial coordinate, because we are talking about one-dimensional heat flow. So if one-dimensional heat flow, then our temperature varies with only one single spatial coordinate, which is x. It doesn't vary with time. That's the reason why I can say that the temperature distribution across one phase, which is this particular area the heat flux crosses perpendicular to, has constant distribution of what? Temperature. That is what I'm trying to say. That particular phase has constant distribution of temperature. So I can say that phase is at temperature T1 and this phase will be at temperature T2. So viewing it from here, I can say this phase is at temperature T1. This phase will be at temperature T2. The reason why it is down because that is temperature keeps on decreasing along the heat flux direction. But then we don't know whether if it's a straight line or with a curve. So let me do this for a general condition. So this will be this will be our temperature function with respect to the axis. And as I said, this is my this is the thickness of my wall. The thickness of my wall. Now, according to our formulas, you see they are actually in differential terms. So what does it mean? For small dx is basically the infinitesimal thickness of our, that is infinitesimal block we use for the derivation of the equation. So for small dx in the thickness, you're also going to get a small change in temperature dt dx, and the heat flow is from here to here. That is simple. That is simple. Now, what then do we do? Let us derive the equation. Now, we will do it. We are actually going to use two methods. One is an alternative method. So just in case you're asked in an exam to prove or show that is for heat transfer through a plane wall, given all the assumptions, this is the formula for the conductive heat transfer. So what do? We've been given certain assumptions. We're told that one, we have a what? A steady flow state. That is one. We have a what? Isotropic material. We have internal volumetric heat generation is 0. And we also have one-dimensional heat flow. So let us do the analysis. One-dimensional heat flow. So we know already that for a material to be isotropic, for isotropic material, the conductive, that's the conductive heat transfer equation is, that is the Laplacian of the temperature field, plus G, that is the volumetric heat generation within our control volume, is equal to 1 over alpha del T del small t. Now from this equation, let us apply the various assumptions. Now we're told that no heat generation within our control volume, so J dot is 0, right? That is, we have a steady flow state, so del T del X, del T, that is the time rate of change of the temperature field with respect to time, the time rate of change of the temperature field goes to 0 because you have a steady flow. So G goes to 0, del T over del small t also goes to 0. Then what else? We also told the material is isotropic, which you've already observed from this equation. It is isotropic. And it is also one-dimensional flow. We'll come back to the one-dimensional flow. So our equation reduces to, that is, the Laplacian of the temperature field is equal to, that is 0. The Laplacian of the temperature field is equal to 0. This is a pure Laplace equation. Then we can say that del squared, that is, of the temperature field, del x squared, plus del squared of the temperature with respect to del y squared, plus del squared of the temperature with respect to del z squared is equal to 0. And since we have, that is, a heat flux flow along one particular dimension, that is, our temperature field varies with one spatial coordinate, then the other, the double derivative of, that is, the temperature with respect to the other axis or the other spatial coordinate goes to 0. So we then have del squared T del S squared is equal to 0. So this is the heat transfer equation, that is assuming all the assumptions hold. This is what we are to use for the derivation of our equation. Hope we are clear up to this point. Let's move on. So for the derivation of our equation, del squared of the temperature field del x squared is equal to 0. Now what can we do? We can apply integration. So let us integrate. Integrating this, what do we end up with? Integrating both sides, we end up with del t. But then there's one thing I want to do. Let me show that first. Now, del squared t on del s squared can be written as del squared, that is d squared dt. And we already know why. I believe we know this from multivariable calculus. Why? Because initially we said the temperature, if you have a steady state, then the temperature is a function of all three spatial coordinates. Then apply multivariable calculus, my dt becomes del t del x as constant, holding y and z constant, dx plus del t del y holding x and z constant, dy, plus del t del z holding x, y constant, dz. Now there's one thing you need to know. Since for this particular scenario, temperature, as I said, is only a function of one single spatial coordinate, which is x, then the partial derivative of, that's the temperature for with respect to the other axis, goes to 0. So what will my equation be now? That's dt is equal to del t del x holding y and z constant dx. The others goes to 0. Then I can divide both sides by dx to get dt divided by dx is equal to del t del x holding y and z0. So this is basically your what? Del t, del x. Then I can replace del t, del r with respect to dt dx. Then I can say that my del squared t del x squared is equal to d squared t dx squared as simple. That's the reason why I'll be making that substitution. Yes, so let's proceed. So I can say from here d squared t dx squared is equal to 0. Integrating both sides, what do I get? If I integrate both sides, I end up with what? I end up with, that is dt dx. The integral of 0 is what? That is a constant. Integral of 0 is a constant. Then what can I do? I can solve this differential equation as dt is equal to c dx. Integrate both sides. What do I get? Let me continue from here. What do I get? I end up getting, that is t is equal to cx plus c. So let me name the first constant as c1. c1. The second constant to be what? c2. As simple as that. Now, what do we have to do? The only thing left for us to do is to apply certain boundary conditions. Now, after drawing my plane wall, what did you realize? You realize that this particular phase was at a temperature T1. This particular phase was at a temperature T2. Now, the thickness was what? L. Then I can say that if my axis is something like this, where here is T and here is my X, then I can see that this particular side is 0 and this particular side is what? L, right? So at temperature T1, what will be my X? Temperature T1, what will be my X? My X will be 0. So I can say at, that is T is equal to T1, my X is equal to 0. At T is equal to T2, here, this face is T2. What will be my X? My X is basically the thickness, which is what? L. That is so simple. Now, I perform the substitutions. Then I can say that, that is, what is the equation? Yeah, T is equal to C1X plus C2. So, that is T is equal to C1X plus C2. So, for T is equal to T1, our X is what? 0. So we end up getting T1 is equal to what? C2. That is 1. Also that is for the same equation, for T is equal to T2, my X is equal to what? L. That is it. So that is T2 is equal to C1L plus C2. And my C2 is what? T1. My C2 is T1. Then I can say from here, the constant, I know this particular constant. I'm finding C1 as well. C1 is equal to T2 minus T1 on L. T2 minus T1 on L. Now, what do I do next? Then I know the equation. I can substitute them inside. All right. Right now, I'm solving the differential equation. So I know C1 is equal to T2 minus T1 on L. I know C2 is equal to T1. And the equation was T is equal to C1x plus C2. So substitute this into the equation. What do we get for the equation? We end up getting T is equal to, that is C1, which is T2 minus T1, all on Lx plus T1. As simple as that. That is the equation we have. So you can see that mathematically. You realize that is the temperature, right? The temperature variation with X is actually a what? That is a partial variation, or if I should say a linear variation along the what? Along the heat flux flow. So that is temperature variation along the heat flux flow is linear. Temperature variation along the heat flux flow is linear. Yes. Now, you remember from Fourier's law of conduction that if you have, say, Q, right, Q dot. So Q dot is equal to what? Q dot is basically equal to, that is negative K A del T del, that is X. But as I said, for if your temperature is a function of only a single spatial coordinate, then your del T is the same as what? dt dx. So Q dot is equal to negative Ka dt dx. Then what can I say? Then what can I say? Then what can I say? Then I can say that now, what was the equation? T is equal to T2 minus T1 on L x plus T1. So I substitute that into the derivation. I mean differentiate. I want to find dt dx from that particular equation. So as I said, T is equal to T2 minus T1 on L x plus T1. So dt dx will be what? T2 minus T1 on L plus 0. So dt dx is the same as, so I can substitute in that expression, negative Ka T2 minus T1 all on L. What do I end up with? I end up with Q dot is equal to negative K, that is, negative Ka T2 minus T1 on L. Then I can say my Ka multiplying T1 minus T2 on L. Yes, because that is, if the negative 1 multiplies this, we end up with this expression. So this is what we can say. This is what we can say. So my Q is equal to K A, that is T1 minus T2 on L. T1 minus T2 on L. That is all. So for plane walls, the conductive heat transfer equation is Q is equal to Ka, that is T1 minus T2 on L. That is it. So this is the equation we'll be using for the questions coming. Now, alternatively, we have another way of deriving this, if you mind, from that same Fourier's law. Q is equal to negative K, that is A, del T, which I said since our temperature varies just a single spatial coordinate, you can write as dt dx. Now, this is a differential equation, so you can just solve it. So Q dx is equal to negative Ka dt. Integrate both sides, that from 0 to L. Dx is equal to negative K and A are constant. Integrate dt from, that is T1 to T2. What do we end up with? We end up with QL is equal to negative Ka. That is that is T2 minus T1. Then what are we getting? Q is equal to Ka T1 minus T2 all over L. Yes, all over L. So this is also another way of deriving the equation. So yes, I think we are done up to this point. Yeah, so I'll come back with problems on plane walls. Have a wonderful afternoon.